Hey physics students, this is Mr. Scott and this is your projectile quiz prep file. Just in case you ran out of time in class and didn't get a chance to review it, or you just didn't understand it the first time and you want a little bit of a refresher, we're going to go through the two round tables that are going to look the most like your quiz and hopefully give you some extra explanation on how to do the problems. So there's three types of problems in this chapter, and you have to know which one you're looking at, because otherwise if you apply the wrong equations to it, you could easily lose all the points on the quiz or test. So you have drawing problems, you've got vector right triangle problems, and you've got projectile problems. Make sure you identify the right one. Here we've got Mr. Hendrickson, a farmer, a fox, a chicken, and some corn in a boat. And they're all going to go across the river, right? And the river is blowing them south at 2 meters per second. The farmer can row 3 meters per second to the east. So we want to find the exact speed of the farmer's boat on its actual course. Ask yourself, is this a projectile problem? Is something flying through the air with only gravity acting on it, making a parabolic arc? No, okay, then it must be a vector right triangle problem, and we have to use just constant velocity equations and set up a picture to start. So I set up my picture here, and now I have to draw the resultant. Using the tip to tail method, we add them up and we draw the resultant, and that should be the actual velocity of the boat after the river's been pushing on him and he's been rowing due east. So we have two legs of the triangle, and we solve using the Pythagorean theorem for the last leg, and we end up getting a velocity that's bigger than 3 and 2 meters per second, which is good because it should be. It's the hypotenuse of our triangle at 3.6 meters per second. Now, because this is vectors, we only ask you for the magnitude of the velocity in the last problem, and this time we're going to ask, well, what angle was it actually going 3.6 meters per second? If we don't ask you this on a quiz, but we do ask you for direction, we expect you to calculate the angle, just like we're doing here on number 2. So using the same diagram from the first problem, let's go ahead and set it up and solve for theta. Now you could use sine, cosine, or tangent here, it all would work, but because we rounded that 3.6 meters per second in our last calculation, and the 2 and the 3 were just givens, let's go ahead and use tangent here because we know that 2 is the opposite, 3 would be the adjacent legs of our triangle, and it'll be a little bit more accurate of an answer. Okay, so we set up the trigonomic relationship, we solve for theta. Make sure your calculator is in degree mode and not radian mode when you do this. Otherwise, your answer will look like a negative or something less than 1, and you don't want that. However, there is one thing that I'm still missing from my answer. I've labeled it 33.7 degrees, but I still need to tell where that 33.7 degrees is going in reference to the triangle, so I'm going to add in the direction. Now there's no confusion about exactly where that 33.7 degrees points. Alright, on to number 3. Now this is the most common mistake year in and year out when we do these types of problems, and that is when kids do not align the displacement and velocity vectors before plugging into their equation. So here the question asks for how long, right? That's time. So we need to figure out the time it's going to take our boat to go across the water. And we could do this in many different ways and still get to the same answer. But the easiest way is to use that 150 meters wide that is given in the problem and then plug it into your constant velocity or average velocity equation, v equals d over t. So do a little algebra and solve for t using your v equals d over t equation, and now be careful when you plug in. So we need to make sure the displacement and the velocity are pointing the same direction or this equation is not being used correctly. Note that I put a little e on the displacement and the velocity to represent that this is the displacement that's going east, and I need the velocity that goes east too. So I plugged in 3 meters per second and not 3.6 meters per second, which is a common mistake. And you get the time at 50 seconds. So on the last part of this problem, it asks how far downstream is the boat when it reaches the other side. So you have to know here before you can even start the problem that we are talking about this distance right here. I'm going to call it DS for D south, right? And that's also the initials of some cool guy I know. But once you figure out that that's what you need to solve for, now you can go ahead and use the same exact equation that you had before because it's going to be moving at constant velocity in that direction, but you got to make sure you use the 2 meters per second as your velocity because it points in the same direction, and this is a vector chapter where direction matters, and we make sure we plug in the v and the d that point the same way. Now this time I'm going to show you a different equation, which actually ends up still giving you the exact same answer you would get if you used v equals d over t. So we use our displacement equation that has acceleration in it, but because we know we're going a constant 2 meters per second south, we don't have to worry about the acceleration because it's just zero. There's no change in velocity. So that part of the equation, the 1/2 at squared, goes away, and now we can just substitute in what we know, the displacement and the velocity, but make sure they point in the same direction. Knowing the time before, we solve for ds and it's 100 meters. Alright, and on to the projectile problem. So you're going to see a vector right angle problem. You probably have to do a drawing or two. And now the piece of resistance, the projectiles, which, because of the acceleration, have the most variables and the most complicated equations. Let's do this. So the amateur physics student is going to first read a problem like this, where we have a baseball popped up in the air with a vertical velocity of 40 meters per second, and we want to solve for the time how long is it going to take to come to a stop at the top of the arc. And the amateur physics student is going to say, well, I can just reason that out. Gravity's 10 meters per second for every second, going the opposite direction as the ball's velocity, so I just need to take off 10 meters per second for every second until I hit zero, which is great. Unfortunately, it only gets you 1 point on a test. So show your work always, kids, and because we haven't messed with displacement at all in this problem and nothing's been given to us yet, we just need to use our acceleration equation rearranged for final velocity, and let's plug in everything we know to solve for t. So I went ahead and put in a y here for all the vectors in the equation just to remind us that it's only the vertical motion we're talking about, and then also put in a 0 for v final because that should be the velocity at the top of the path. Then plug in 40 meters per second for your vertical velocity initially, and then make sure that you have gravity as a negative 10 meters per second squared, because this positive 40 meters per second points upward, and therefore anything that points down like gravity has to be negative, because that's how we're defining direction. Do a little algebra and divide 10 back over into 40, and you get 4 seconds as the time that it takes to get up to the top of the path. So number 2 tells us that the horizontal component is 5 meters per second, and then asks for what the total velocity is. Typically in these problems, we'll give you the actual velocity and the angle that it was shot up at the ground from, and then ask you to figure out the components. Well, in this case, we're going to reverse, so because we know two sides of a right triangle, we can redraw this and have 5 meters per second on the bottom, 40 meters per second on the top, tip to tail, and then have our resultant be the actual velocity of the ball. So once again, we use the Pythagorean theorem to solve for that actual resultant, which is the velocity of the ball, and we get 40.3 meters per second. So on question 3, it asks, what is the total time in the air? And now you have options as a student. You can either explain this in words and say that, well, gravity is the acceleration, so it's going to take the same amount of time to bring the ball to a stop, going vertically as it would to fall back down, the same displacement to the original height that it was at, and you can just double the time. Or you could actually show your work, and we could plug into a displacement equation here or an acceleration equation, but instead you can also just make it simple and show that you have 4 seconds go up, 4 seconds go down, they're equal, the time up and down, and then add them together, you get 8 seconds total. Then the last problem asks, how far was the shortstop from the hitter when the ball was caught? So if you don't realize up front that this is dx that we're going to try and solve for, then you're probably going to be pretty lost on this problem. So that's a displacement, that's the horizontal direction of motion. We're going to eventually need to plug into the only equation we have in the horizontal direction of motion, which is vx equals dx over t, and then solve for dx really quick. Now substitute in what you know, and from the previous problem we know Vx is 5 meters per second, because that's the horizontal component of the velocity that was originally hit with, and that stays constant. And then we also know that this is the total time in the air because it's going to eventually hit the shortstop after 8 seconds, so we have to make sure that's the time we plug in. Once you do that, you figure out that the distance away the shortstop was 40 meters, and the ball was caught out. Alright kids, that's it for the tutorial. Harry Carey is proud of you, and if you don't know this man, he is kind of a big deal in baseball. I'm here to educate. So he was the old announcer, and he made the 7th inning stretch what it is. They still honor him at every Cubs game. Respect. Respect. See you next time.